we can now ask a bunch of different questions, and now we actually, and particularly in the architecture questions, about what do we mean by FPAs, particularly compared to FPGAs. And to do that, I need to kind of explain a little bit of what you typically see with FPGAs. Because what you might imagine with FPGAs is that you're going to have your CLBs, which are your computational logic blocks, and routing. And you get sort of a structure like this, and we will get more into the routing in other conversations. But in this case, you have a number of blocks and routing. We just assume that everything gets compiled from there. And you could imagine a very similar case in an FPA where you could have CABs, which are computational analog blocks, or CLBs, and routing and connect all of them together. Makes sense. What is there to say about architectures? Well, when you look at FPGAs practically, they look different now. In most of the chips that you'll find, there'll be other specializations. So in addition to a whole bunch of CLBs, you'll have optimized elements for multipliers, say 16 by 16 or 18 by 18 bit digital multipliers. Because one of the things that in computing that is so needed is to multiply numbers, actually multiply and add. This is the core in all vector arithmetic, the core in doing all sort of matrix algebra and so forth. So things tend to be optimized in not just thinking single ones, but whole groups of them, right? And so not only do you have multipliers, but then you build a whole range of maybe additional coefficient RAM of some sort, so that way you can hold all those extra things, all those extra variables you're going to be multiplying against. And so this works out really well, and almost always you see specialization in every FPGA. In fact, it's very common for multiple FPGAs to even have processors hard embedded in them, and all sorts of other functions. Different size of different elements. I mean, otherwise you go, well, why wouldn't I just have 5 or 10 FPGAs and I'd be done, right? I don't need, but if I look at a data book, or now just all online, but the equivalent of what a data book years ago, you'd see thousands of chips coming from a company like Xilinx or Altera or all of their sort of developments. So you ask the question, well, okay, why? And the main reason is it's these kinds of specializations that are kind of used for different applications. And it's very easy to build these structures when you have a configurable framework around it to begin with. So for an FPA structure, you say, well, that's great. What would be the specializations? And that's actually an interesting question, because you could have microprocessors and other components. But further, I just want to go back to this vector matrix multiplication question, because you might ask, well, how would I maybe do that support in an FPA? And here's where it gets interesting. Depending on the routing infrastructure, and it's entirely a question of the circuit structure you build, you could build a routing infrastructure where if these are all single floating gate devices, and you can use single floating gate devices to be perfectly good switches, if you do this, then all of a sudden now I've got this interesting crossbar network to work with. That's just part of my routing. But I also know, going back to even like the original single transistor synapse work, that going back in the 1994 timeframe, I know that this also allows me to do other functional computations like vector matrix multiplication. Aha, exactly what we're doing here. And you think, oh, wait a minute, that's actually pretty interesting. Where do I store all the coefficients? All the coefficients are being stored right in the charge in the floating gate. So there's a charge here, and that charge will stay there. This is sort of that classic sort of circuit you're supposed to avoid, which is because it has no DC path to ground. It has no DC path to ground, meaning it actually has charge storage. And this is a phenomenally useful circuit as you look at some of these capabilities. And so you can actually have not just a 1 or a 0 turning the switch on or off, but you're going to have a whole continuum of values in between at very, very high precision all the way through these devices. So this really allows you to say I can get programmable and configurable components, often the same components. The floating gate circuits concept, to kind of review this, allows you to have a programmable memory. The transistor, though, itself is also used for computation, so it's like having a gate voltage with a programmable parameter in it. And I can even imagine doing adaptation with it, which depends on what I utilize or how I built my architecture. This is sort of a classic picture of how you would build such a circuit in using just single poly. Very traditional, always guaranteed to work kind of structure, not the most optimized, but that's okay. Optimization requires a lot more understanding of what process you're working with, but a structure like this seems to work across processes that we've seen from 2 micron in one form or another, from 2 micron CMOS down to 14, although you got to be a little more careful with, say, things like FinFETs and stuff, but it all kind of holds. And you can definitely find that you get 10-year lifetimes. You can also then do precision programming and programming of this, because you go, well, if I could store something for 10 years, how on earth am I going to change it? And I use different processes like hot electron injection for my precision programming. It works extremely well, and it guarantees I get perfect isolation or near perfect isolation, as well as processes like electron tunneling to just kind of erase and clear things. But the implication of this is huge, because where normally I would have to use a huge amount of infrastructure to kind of do matrix vector multiplication and all sorts of other things in an FPGA, which I'm willing to do because it does have some really huge advantages. Here it just simply happens in the routing, in the connections between things. In the dead weight, that just simply gave you configurability. And here I get all of this directly. So it's an incredible opportunity, an important thing to kind of notice what you can do when you actually utilize all the physics of the devices.